Okay. Welcome back. So, I just wanted to go through some of the basic things about like a few of the basic things about solvable groups. So here are some of them. So let me just tell you the main properties of solvable groups. I guess we could call this a theorem. Okay, let G be a solvable group. This theorem has different parts. Let H be a subgroup of G. Then H is solvable. 2. Let G be a solvable group. And let N be a normal subgroup. And G mod N is solvable. Three. Let G be a group. N is a normal subgroup. And suppose N and G mod N are both solvable. Then G is solvable. And fourth thing, suppose G1, G2 to Gn are all solvable. Then G1, the direct product is also solvable. Good. Okay. So probably, so we definitely have the power to prove all of these things. But I don't think I want to do that. Okay, so let me prove with all the details, let me prove 1 and 4. And let me just give you a sketchy proof of number 3, which is kind of like the hardest one, I guess. Okay. And you can see like this gives you a lot of ways now to kind of build solvable groups or to find out if a group is solvable. You know, basically you start with like some big group and you try and find a normal subgroup. And now you can determine if G is solvable by just proving that the normal subgroup is solvable and the quotient G mod n is also solvable. That tells you that G would be solvable or not. Okay. Of course, if you find no normal subgroups, then G is going to be a simple group. Simple groups are, well, you know, it depends, but we'll talk about that after, I guess, what it does, what simple groups have to do with anything here. Oh yeah, let me talk more about that after. Okay, so let's prove 1 and 4 in all the details. Start with 1. Okay, a G be a solvable group. Okay. And our claim is that the nth commutator of G is trivial for some n. Okay. And actually, so we can prove something stronger than that. Let's take our abelian series for G. Let this be an abelian series for G. Then we can show that not only that, we can show that the ith commutator is contained in GI for I equals 0, 1, 2, all the way up to n. Okay, and since G, the nth term is trivial, this formula will tell us that the nth commutator is contained in a trivial subgroup, so it's trivial. Okay. Now, if you happen to also be taking set theory, you'll notice this is a prime example of when we want to use induction, but we can't, we have to stop at some point. So we need to use like finite induction. Okay. So we're going to prove this by induction, except just like finite induction. Okay. We proceed by induction. So the zeroth commutator is just defined to be G by convention. And G0 equals G. So this establishes that this, in other words, the base case. Now assume that for some I, 0 less than or equal to I, strictly less than n, that we have GI contained in GI. So the ith commutator is contained in the ith term of this abelian series. Okay, and here this n, yeah, okay. Okay. So what do we do now? Well, we want to show, let's just, what do we want to show? We want to show that GI plus 1, sorry, the ith commutator, the I plus 1 commutator is contained in GI plus 1. That's what we want to show. And what facts do we have at our disposal? We have the fact that GI plus 1 is abelian. Okay. We also know that this is contained in GI. Okay. So one thing we could try and show to establish this, we could try to show that let's see, we could try and show that let's see, we could try and show that GI plus 1 was abelian. If we could do that, that would tell us that this is contained in GI plus 1. Okay, but that doesn't quite work because we don't know that G. Actually, does that work? Okay, so to do this, we need to show that GI plus 1 is contained in GI. Okay. So, okay. So let's just try to do some different things. You know, GI mod GI plus 1 is abelian. That tells us that GI plus 1 actually contains GI prime, the commutator of GI. Because, well, I'll just write that fact down here. If G mod H is abelian, that implies that the commutator of G is contained in H. So here, GI mod GI plus 1 is abelian, so the commutator of GI has to be contained in GI plus 1. Okay. So now if we look at the commutator of the ith commutator, that's just GI plus 1. Right? Because G with I means G with I primes, and then I just add another prime to it, so that's I plus 1 primes. Okay. Now, GI is a subgroup of G sub I, and that's contained in GI plus 1. Okay, that's showing that, okay, that we're all good. This proves that for as long as I is less than n, then and GI is contained in G sub I, then GI plus 1 is contained in G sub I plus 1. And then by induction, by finite induction, really, for all 0 less than or equal to I, less than or equal to n, GI is a subgroup of G little I, so therefore the nth commutator of G is trivial. Okay. And that is the end of the proof of what we claimed. Okay. But now if we go back, I wanted to show that any subgroup of a solvable group was solvable. So we had H is a subgroup of G and G is solvable. Now what we just showed implies that the nth commutator of G is trivial, but the nth commutator of H is going to be contained in the nth commutator of G. So the nth commutator of H is trivial, so H is solvable. Okay. Okay. So if you have a solvable group, any subgroup of it is solvable. Let's also prove that the direct product of solvable groups is solvable. Okay, for that we need a lemma. Let's take groups H and K. Then the center of H cross K is just the direct product of the centers. Okay, what we really need is the second one. So let's prove that, but these things are both true. The one can be an exercise 2. Okay. So what should we do? Well, maybe just let's compute the commutator of like some element of H cross K. Let's do the commutator of HK with H prime K prime. Okay, the definition of the commutator is just, we do HK times H prime K prime times HK inverse times H prime K prime inverse. Now, because we're in a direct product, how do we multiply things? Well, we just multiply things like first coordinate, multiply first coordinates, and multiply second coordinates separately. So what we have is that when we multiply all these four things together, in the first coordinate, we just have the product of the first coordinates. And in the second coordinate, we have the product of all the second coordinates. Okay, in other words, this is a commutator of H and H prime. This is a commutator of K and K prime. So any commutator of things in H cross K is a commutator of something in H with like in the first coordinate, second commutator of something in K in the second coordinate. Okay, and then this is enough to see so this is enough to see that you get this direct product. Because any commutator is just a direct product of two commutators. Okay. Now we want to show that the direct product of solvable groups is solvable. So this is part 4. Let G1, G2, up to GK, Gn be solvable. So then like G1 to the E1 is trivial. G2 to the E2 is trivial. And so on. Gn to the En, that's trivial. Okay. And let M just be the maximum of all these E's. Then G1. So if I take the mth commutator of this direct product, well, that's just the direct product of all the commutators. And each of these is trivial since m is bigger than each exponent. And that's the trivial group. So in other words, G1 cross cross Gn to the m is trivial, so it's solvable. Okay, and now I just wanted to sketch for you the third part. 3, just a sketch. We're given n is normal in G, n solvable, and G solvable, or sorry, G mod n solvable. Okay, so we write G bar to be G mod n, and we're given that G bar to some n is trivial, and we're also given that n bar to some m is trivial. And the claim would be that G to the n plus m is also trivial. Well, because then that would prove that G is solvable. Okay, so first of all, you can say that n is contained in, or sorry, you can say that G to the n is contained in n. That's because G bar to the n is trivial. But then we just do the same thing that you just do the same thing as like we did before. Well, if the nth commutator is contained in n, then the n plus first commutator is just contained in n prime. And just keep on going. Well, G to the n plus m, that's contained in n to the m, that's trivial, proving that G is solvable. The end. Okay. So that is just like kind of a quick tour of kind of like the basics of solvable groups. I didn't really tell you what they're for. So I'll just spend a few minutes. Like the first thing we can say is that kind of like they're kind of like the anti-simple group. So just as an example, let G be a solvable group. Then if G is simple, then G is cyclic of prime order. So the only solvable groups that are also simple are just like cyclic groups of order P, like cyclic group of order 5 or stuff like that. Okay. So if G is simple and non-abelian, it cannot be solvable. Okay. Proof. Well, G is simple if G is both simple and solvable, then G to the n is trivial. Okay. But G prime is normal in G. So either G prime is trivial or G prime is the entire group. Because G is simple, its only normal subgroups are the entire thing or the trivial subgroup. Okay, if G prime is trivial, that means just that G is abelian. If G prime equals G, well then G prime prime is just G prime, which is G. So if G prime equals G, then G prime prime equals, well, that's just the same as G prime, which is G. And so G to the N is also G, which is a contradiction. Okay, so it has to be that G prime is trivial, which tells you that G is abelian, and the only abelian simple groups are the ones that are cyclic of prime order at the end. Okay. So like simple groups and like solvable groups. In fact, you can even say that if G is a group which has a non-abelian simple group as a subgroup, then it can't be solvable. Okay. So you can do stuff like that. Okay, so let me just make a quick note of where the term solvable comes from. Well, solvable comes from solvability by radicals. In other words, trying to see which equations, you know, have like can be solved with you know, with I guess it's called surds. Okay. Given an equation x to the n plus an minus 1 x to the n minus 1 plus dot plus a1x plus a0 equals 0, and you write the solution using nth root signs, plus, minus, divide, times, and like a1, or sorry, a0, a1 to n minus 1. And the solution to this problem involves like rewriting the conditions for this to be solvable in terms of like all these algebraic stuff, to rewrite that condition in terms of basically solvable groups. Okay. So somehow the fact that you can write a solution in terms of these operations means like some group action on the roots corresponds to a solvable group. And we'll see a little bit of that later on. Okay. Okay. Okay, and then I also wanted to mention to you this theorem, which tells you like this. To me, this is like interesting. Okay, it says let G be a group of odd order and G is solvable. Okay. Which I just think is pretty interesting. Okay, so let's just take a break now for until for just 5 minutes. Okay. When we come back, it's time to talk about rings. Well, part of the point of that will hopefully work up to talking about stuff like this. Okay, so yeah, I'll see you guys in 5 minutes.